Good morning, everybody. My name is Nicholas Buckberg. This is the Bearmax Critical Design Review presentation. We are Group 28. This is for our Bearmax, the Social Emotional Learning robot. So our team members are as follows. We have Rahim Khan in Computer Engineering, Zachary Larson, also in Computer Engineering, Bhavani Sivakumar in Mechanical Engineering, and myself, Nicholas Buckberg, also in Mechanical Engineering. Thank you for joining us, and let's get right into it.
Bearmax is a robot designed to help people with autism spectrum disorder to recognize and understand various social situations. Therapy robots are used in the medical field for a variety of different reasons, including teaching children with ASD to identify emotions. This is the second iteration of Bearmax. One of our main goals is to expand upon the successes of the first version. Some of our goals include to add more emotions and a larger range of these emotions that Bearmax can express, which users can learn and recognize. We also want to upgrade the electrical system and mobilize Bearmax. We're also collaborating with the computer science team to have additional methods for users to communicate with Bearmax, either through the app or through a touchscreen.
Our specifications are as follows. The max volts we can use is around 12 volts. Our speed range is 1 to 5 miles an hour. It isn't exactly critical for it to go very quickly, as this is a therapy robot first and foremost, so as long as it is able to move at a moderate pace, that is sufficient for our goals. The weight limit is highlighted as it is a critical design criteria for us. Contrary to last year, our robot will be able to move, not just through physical expressions, but across the floor translationally. This makes the weight more important. A heavier robot, more difficult to move, it'll move slower, or possibly not at all. So trying to keep it under 20 pounds is our goal. Height limit is important for the possibility of it tipping over. That's a big safety issue. You have to make sure we stay below 2 to 3 feet, 3 feet being the maximum. Our minimum response time to input from the Jetson, we hope to keep below 5 seconds. So whatever the Jetson detects via CS team's work, whatever emotion it detects, our response time from that input should be less than 5 seconds. We're hoping for a minimum run time of at least 20 minutes. Again, like I mentioned, we're going to be very mobile this year. We're not going to be plugged into a wall outlet, so this makes things like runtime much more serious to consider because we don't have this constant supply of power. We're limited by whatever amount of power is in the power pack device attached to the robot. On the right, you'll see our degree of freedom range of motion chart for each limb. This is another critical design guiding criteria because it is how we objectively break down how each component will display emotions. So knowing each joint and its range of motions was something we decided on very early. The only major difference from last year is the platform, neck, and fingers. Aside from proportions and sizing, most of the designs for shoulders, elbows, and ears will remain very similar. Fingers is a completely new design that Bhavani started from scratch. Neck is a modification to an existing design that is much simpler than last year's. We hope this will eliminate a lot of the issues last year had with integrating the neck into their final design. It slowed up a lot of things because their design was too complicated, so we hope this much simpler neck design will carry over easier.
As we mentioned before, we're continuing this project from last year's version. The concept design for our version is shown in the bottom picture. Taking some of the successes from the previous Bearmax, we're increasing the amount and variations of different emotions, modifying the neck design, and mobilizing Bearmax through a track system so it can walk alongside users or just have more movement in general. Another change we're making is the neck. The new neck design is based on an animatronic or a puppet, so the movements of Bearmax's head can be more realistic to that of humans. Along with more expression, the camera which will be on Bearmax's head can also follow the user's movements and show that Bearmax is being attentive. The neck will not only act as a platform for the head, but also has the shoulder, arm, and hand connections. The base of the neck, which is a cylinder, is a PVC pipe that will be connected to the platform in the bottom picture. This will then be placed on a track so the robot can move. We'll also be adding hands to the robot. Instead of 5 digits like a human hand, we're having a paw and a thumb. Now it's time to discuss the specific components and the manufacturability of the robot. Selecting the right motors for the movement of the parts of the robot is very important. Many criteria among these listed in the tables were considered. DC motors, while their voltage supply is easily adjustable, it's difficult to control because they rotate continuously. Stepper motors have a higher degree of control compared to that of DC motors, but their torque decreases when speed increases. Stepper motors also do not require encoders. And finally, servo motors. While servo motors require encoders, they have a higher torque at higher speeds and thereby increased precision. They're also lightweight and typically have varying voltage options. So, at the end, we chose servo motors for controlling the movements of Bearmax. Similarly, we needed to consider materials for the shell or exterior of Bearmax. While researching other therapy robots, they often use softer materials, and their appearances are similar to that of stuffed animals or toys, and this is to make children feel more comfortable. Our goal is to do the same. So while we want to ensure the skeleton's durable, we want to have the exterior being soft. Last year's version used TPU, but it was less malleable than expected, so we wanted to try and implement 3D printed flexible resin. While the durability might be less than that of rigid materials like PLA and TPU, as seen through the tensile strength, the skeleton will be made of PLA, and we think this is sufficient amount of durability. Also, while flexible resin is very expensive, we're lucky to have this particular resin already in our lab and plan to use it to construct the exterior of our robot.
So for our hardware design, we are planning to incorporate a rechargeable power bank, which will be used to power a custom-made power distribution PCB through a cable. This PCB will then power a motor driver through regular wires, and it will also power the Arduino Uno and the Arduino Mega through wires soldered on, and it will even be providing ground to these two as well. Now, finally, this power bank will also be able to charge the Jetson, and it should just plug in through a regular cord. Now, the Jetson will control the Arduino Mega and will just use a regular USB serial port communication. The Arduino Mega will be controlled by will control the Arduino Uno and will be connected via a UART configuration. I also should mention that the power distribution PCB will also power the individual components, including the neck servos, LCD eyes, and the arm and torso servos. These servos and LCD eyes will be controlled either by the Arduino Mega or the Uno, and these will just be plugged in. Now, the Uno will also power and connect to the Bluetooth module, which will also give controls to the motor driver. Essentially, whenever the outside app sends remote control commands to the Bluetooth module, and thus the Arduino, it will send the right amount of controls to the motor driver.
To begin our hardware comparison, we'll start by looking at the motor drivers that we considered for the Bearmax project. And just starting off with the one we chose, it's a simple H-bridge just pictured above, can control 2 motors per unit, and it can take a 5-volt power supply or a 12-volt power in and ground, and then a couple logic inputs from the Arduino in order to configure. And the main reason we chose this was availability. It was already available to us within the lab, the Wear Lab that we're sponsored by, and it's just the easiest to test with and to use. So for testing, as of right now, we've continued with using this. And then the other 2 parts, starting off with the first one, is a solderable chip in the smallest form size, and would be like soldered directly onto a PCB. which we have planned for the future in case we get that far with controlling it, if we decide that the H-bridge is not reliable enough. And the middle part, you can see, is the most expensive, and it can take the highest range of voltage. And that's because it's a full development board used for professional robotics. And it seemed too complicated for the purpose of it. So we went with the simple H-bridge. Moving on to the power supply. The main concern here, because there were a lot of parts that we'd seen that could provide the 12-volt power out and the amount of watts we needed and current. But the real limiting factor between the real factor that we were looking for was size and weight. Because we have to keep the footprint and the weight of Bearmax under about 20 pounds is our specifications. So really, that's what it came down to. And the fact that the other batteries are technically a little bit more powerful doesn't really matter. For our purposes, the Talent Cell rechargeable power supply should be all we need. As it comes to the voltage regulator, all three of these can accept a similar range of voltages, as you can see, from about 2 to 15 volts is what we needed. And this would be used in our PCB that drops down our 12-volt input to 5 volts to power the voltage rails for all the motors and the LCD eyes and stuff like that. And what we can see, the main draw of the part that we've chosen is the current out is what we need. Since the robot will be controlling a lot of motors, actions such as waving or like moving the neck to look at the user take a lot of motors and may take a lot of current to actually execute. So we wanted to make sure that all the 5 volts could support that. And the part was actually recommended to us by Dr. Weeks. As opposed to the other two, we can see that they only go from 1 to 2 amps of current, and that wouldn't really help us for what we need. Moving on to our Bluetooth module, this will be used as a way to control some of the motors from like a phone app. So specifically, again, the track system has Bluetooth compatibility through an app. So essentially, a user could log onto the app and use their phone to pilot Bearmax and control where he'd go. And we considered using Bluetooth 5.0 with this part here because of the faster transfer rate. But there was some compatibility issues with the actual track part. And then we decided that the Bluetooth is not going to be like a huge part of the user experience. So we didn't really need anything too complicated. So this part was up and working and was actually provided with the track to work. So we ended up moving forward with that. And finally, these are the parts that we'll be reusing from the last version of Bearmax, as pictured here. The main Arduino Mega, as well as the sub Arduino Uno, will be reused for similar purposes to connect to the motors to actually drive the movement, as well as the Jetson Xavier NX, which will act as like the brain of the system, controlling and sending specific actions between everything, as well as the LCD eyes. These are all parts that were used and selected last year, so we decided to move forward with these same parts as well. And then right here we have the connection guide for how the Arduino will connect to various components in the idea of Bearmax. So the main Arduino Mega is connected to a station Arduino Uno. And this is just to support the amount of pins we need for the motors to drive that movement. So the bigger limbs, such as the right and left arms and the neck motors, are connected to the bigger Arduino. And the servo for the spine and the ears are connected to the smaller Arduino Uno. As well as the LCD eyes will also connect to the main Arduino and will feed into the head. And then we have things like the Bluetooth connector to the Arduino and the 5-volt drop down.
Now here are our schematic designs for our PCBs. Now, since we are a team of only 2 mechanical engineering students and 2 computer engineering students, we are allowed to use development boards, but we still need to use printed circuit boards. Just it will not need any microcontrollers. Now, the reason we made this power distribution board is we need to have a way to connect all the different components to the power source without using breadboards. And so our solution is this. The way it works is 12 volts from the power source will be sent here to these pins, which will be sent through this voltage regulator and output 5 volts, which this 5 volts will be enough to power the different servos and Arduinos, which the power modules are attached here, and the ground portions are attached here. Now, the only part that doesn't attach to the 5 volts would be the motor, or the connections to the motor driver, which is here. Because that requires 12 volts. Now, for our motor driver, we have a design that we may use for a stretch goal that utilizes a couple PWD 13F60s. Now, these are essentially H-bridge drivers, which allow the motors to spin forward and backward, so our robot will be able to turn where one motor goes forward and another goes backward, or go backwards or go forwards. The way it works is the power comes in from here along with some data ports, and then the output comes from out here, which this part connects to the motors. The resistors and capacitors here, along with the inductor, are just meant to keep the voltage stable and, organized. Here are the layouts as made in Eagle. Now, here is the overall activity diagram for the robot. First, the robot turns on, then it activates its Jetson, Arduino boards, and all its systems. Then we plan to incorporate an emote where it displays happy eyes and waves hello, because it is happy to see you. Next, it awaits for input. If it receives input from the remote controller, it will move according to the input given. And if it receives input from the mobile application, for example, if the user wants to play a emotion recognition game that I will explain later, it will begin it and run through the game. Now to explain the emotion recognition game. Keep in mind, this is the same game that was developed in the previous version of this project. So we will essentially be reusing it, and we will only make minor modifications, as I will explain later. The way it works is it will search for a face, and if the camera recognizes a face, it will start its game. It will randomly choose an emotion and then perform an emotional expression. For example, if it's happy, its eyes will read as happy, and it will assume a position that makes it seem happy, like it'll raise its arms up as if it's cheering. Similarly, if it chooses to display a sad emotion, it will raise its arms towards its face, looking like it is crying, and its eyes will be more sad to display a sad emotion. Now, the user will, once this robot goes back into a neutral state after performing it, the user then has to perform the exact same emotion. The user has to be, act sad or act happy. If it's correct, it adds a point and starts another round. The purpose of this is to provide a way for users to learn and understand emotional expressions, not only to recognize them, but also to express them back. And the modifications we plan on incorporating will be the eyes. Now for the software. The brains of the robot will be the Jetson. And we also have a companion mobile application that is being developed by a separate computer science team. Now, this mobile application will send sockets to the Jetson. These include some data along with commands for the software design. For example, if the companion mobile app commands the robot to start one of its games, it will send that command via sockets through a Jetson. This Jetson will have that socket info be sent to the ROS2 framework that is incorporated onto the Jetson, and that socket info will be able to tell it different commands and also send data back and forth. This Jetson, and I should mention this ROS2 framework, will be able to send its commands to either the Uno or the Mega. Now, the Jetson connects to the Mega, as mentioned before, through a USB serial configuration, and the Mega also connects to the Uno. And as I mentioned before, the Arduino connects to the Bluetooth module. Now, we do have a Arduino Bluetooth app that we are going to be downloading. That will connect to and control the Bluetooth module, which that module will connect to the motor driver. Now, that motor driver is connected directly to the Arduino. It is powered by the power distribution board, as mentioned before, but it is controlled mainly by the Bluetooth module. Now, other than that, the Arduino Uno, through its commands from ROS, controls the neck servos, and the Mega controls the LCD eyes and arm and torso servos.
So onto some of the software selection. We wanted to select a Bluetooth app that would work to pair with the connector to the Arduino in order to read data and send data to it. And this was kind of an easy decision for us. The cost of the app we chose was free, and it pairs directly to the part. It's actually manufactured by the same company, and will pair directly to the app and send direct feedback, and we can provide input to it as well. The paid app is probably the best in terms of user quality and features, and the tools that you can use are probably useful for developing a larger scale. But as we said before, the Bluetooth is going to be used just to drive that the track system, so we didn't really consider it a huge part of the system. Finally, the programming language we'll be using for most of the code. We basically were just looking for things that were compatible with the most, and it turns out that we have to use C++ and Python. And C++ will mainly drive the Arduino code, as the Arduino IDE is compatible with it. And additionally, we'll have to connect the Arduino to the Jetson and use the ROS library as well to allow ROS to control the motors, as well as the other programs we will need for that. And then Python is actually automatically included with the ROS library so on the Jetson we will need to program in Python and C++. And then C was only really used for the Arduino IDE, so we didn't even really need to use it because C++ is just as easy to use. So moving into the software that will be running off the Jetson, we have ROS, which is the main brain, we'll say, of the robot. Essentially, the Jetson will connect to the Arduino and communicate actions through ROS, which works by setting up client and server nodes, essentially actions, and is a wide library of many different robotics knowledge and actions that you can just use to instantly test larger robotic systems in an easy way. And then the Jetson will also be running through ROS the facial detection software and for the emotion detection algorithms and the emotion game. And then finally, the Jetson has to connect to our CS team's server, and we will use sockets to do that, and specifically socket.io, again, which is more of a stretch goal, but we have begun working with the CS team to see how far we can implement sockets. Yeah, and moving into the administrative content, we have just our budget. So far, most of our parts have been provided by the Wear Lab, by Dr. Park, as well as the senior design inventory. So things such as our servos, the Arduinos, the Jetson, the track were all provided by the Wear Lab. And then the things that we are looking to purchase, or we have purchased, the power supply, the material for our 3D printed shell, and the outer layer of Bearmax, and we're expected to keep this to about $250 as of right now. Yeah, and then here we have our work distribution that we've been using and will be using going forward for like the final steps of Bearmax. And we can see we have our two mechanical engineers, Bhavani and Nicholas, and then the two computer engineers, myself and Zachary. And the mechanical engineers' tasks focus on modeling the last parts of Bearmax and fully 3D printing them, as well as assembling a little skeleton, whereas our computer engineering tasks are finishing the electrical system and working with the programming to integrate the actual movement and interface with everything.
Our team has made considerable progress this semester. Some of the most important goals that we have are to have functioning components of the robot, such as the neck of Bearmax. As you can see in these videos, we've made and tested the neck, which is different from the first version of Bearmax, as it has more degrees of freedom, or movement. We've also tested and printed the prototype of the hands. As you can see, we have a paw and thumb, and the paw moves, the thumb retracts, and can also bend like the paw. The hand prototype uses servos to control all its movements. We also tested the track system to see the maximum amount of load that it can hold. Although we're aiming for 10 pounds, the max limit that we can have is 20 pounds. This is the 10-pound test. And this is the 20-pound test. As you can see from these videos, the larger the weight limit, the slower the track moves. Fortunately for this project, speed is not an important consideration because we want Bearmax to walk along the child. We've also ordered most of the necessary parts for our project, such as the power supply and PCBs for our project. The neck, shoulder, arms, track, and a platform are completed. Our team's also begun working with Ross to program the limbs of Bearmax. Though we're facing some challenges with the Jetson, we're working to solve these issues, among others. Our plan moving forward is to test the hands and torso, assemble the skeleton of Bearmax so the CPE and CS team can begin testing and working on it. Next, the hardware team is planning to tackle the head and the shell of the robot. The CPE team will work with the CS team and also focus on ROS integration and the LCD eye emotions. Our plan moving forward is to test the hands and torso, assemble the skeleton of Bearmax so the CPE and CS teams can begin working and testing it. Next, the hardware team is planning to tackle the head of Bearmax and the shell, and the CPE team will work with the CS team and also focus on ROS integration and the LCD eye emotions.
Some challenges we've experienced throughout the design process for this project include starting from scratch from the hands, completely changing the neck design, and modifying the torso design. Fortunately, we've been able to get considerable assistance from previous year's team in the end, learning from the challenges they experienced so that we can improve upon their design and add some stuff of our own. Unfortunately, the Jensen has had considerable issues on the software side. Fortunately, we have been able to reach out to advisors and experts in the field at UCF to get assistance and move through it. Designing and ordering the PCB has also proven to be difficult, but with extensive work, we have been able to get it ordered, and it's on the way to being integrated into the robot. Some general challenges we have is overall lack of experience. Most of us do not have extensive knowledge in robotics when we started this project, so it's absolutely a learning curve to get started. Fortunately, we started early. We were aware of our inexperience, so designs, issues, processes, we worked very early to get everything done because we knew that we would have to overcome that hump, so to speak. Things such as the neck and the platform were actually constructed before they started senior design too, as well as software involving the eye display on the computer engineering side and PCB research. Overall, we are hoping to finish and be ready for testing by the beginning of March, and we're going to keep with our finishing early strategy because of our inexperience, and we're excited to show you what we finish. Thank you for watching. You all have a wonderful day.